In 9.2, we look at differential equations with initial conditions, and it's really closely linked to 9.1. We're going to need the antiderivative to go from our differential equation to the equation that relates to variables. But then really importantly, if they give us some kind of an initial condition, that allows us to find that value of our constant of integration, and then we can actually give the specific solution that meets both. And you can do this in a variety of different ways. I mean, here they say, you know, solve that ds over dt is equal to 2t, and then they say with the initial, I don't know why they say conditions there, I suppose there's two conditions there, but we could present that a different way as well. And I think it's valuable to see that they could say that s is equal to 3 when t is equal to 0 by telling us that the s function evaluated at 0 is equal to 3. And I think that is an important thing, that at some point you're going to see that they give you that initial condition using some kind of function notation. Now, in order to solve this question, what we're going to do is we're going to use our antiderivative. So if ds over dt is equal to 2t, then with our antiderivative, we can say that s is equal to t squared plus that constant. Now, the antiderivative of 2t is t squared, and if you'd like to, you know, go back to that antiderivative process, I suppose you could have done it as 2 divided by the initial exponent was 1. We're going to add 1 to that, and then again, the initial exponent was 1, so we're going to add 1 to that, and then we add the constant on the outside. Hopefully with that 9.1, you've practiced enough that maybe some of the simpler kind of polynomial antiderivatives are becoming a bit second nature. It is important to get to that point where the antiderivative becomes maybe not as comfortable as the derivative. We certainly do derivatives more, I would say, overall, but you do have to become quite comfortable with that antiderivative process. All right, now I'm going to change this just a little bit because I do think function notation is an advantage. And what this is, oops, that's s is in the wrong place. This gives me the relationship between the variable s and the variable t. So we call it the function s of t is equal to t squared plus c. Well, if s of 0 is equal to 3, then 3 is equal to the evaluation of that function when time is 0. You gotta love when that's 0 because 0 squared is 0, and I get that 3 is equal to that constant. And that's really important that, you know, attaching some kind of, this function is the general solution. If we just had that ds over dt is equal to 2t, that would work for any value of c. But because we have that additional initial condition, then because 3 is equal to c, I would say that s of t is equal to t squared plus 3, and we call that our particular solution. And essentially, it is just the idea that although any constant would satisfy the differential equation, this equation that I'm boxing in red there is the only equation that would satisfy both the differential and the given initial condition. And really what 9.2 is about is basically solving for that constant of integration. All right, moving right along. So another example very similar to that. It wants us to find the function that passes through -1, 0 that satisfies that differential. With the differential, the way that you're using the notation in this case, we have to basically say y, and we're not going to do a lot of manipulation. We're going to do that later when we talk about the integral. But really, if dy over dx is equal to 6x squared plus 6x, then y is equal to, and I'm going to do the full process here, it's the initial coefficient divided by the initial exponent plus 1 times the variable to the initial exponent plus 1. I'm going to do the same thing here, so that's going to be 6 over 1 plus 1 times x to the power of 1 plus 1, and then finally adding a constant. Now, that is a little bit overkill. You don't have to do this each and every time you take the antiderivative. You do have to make sure that you're confident in getting to the point that this is 2x cubed plus 3x squared plus a constant. Now, I would like to remind you at this point that if you're not sure you've done this correctly, then you could use the derivative here. So if I apply d over dx on both sides, I could say that y prime, which is dy over dx, right? These mean the same thing. And that's going to be equal to 6x squared plus 6x, which takes me right back to the given differential equation. Now, they do tell us that that graph passes to the point -1, 0. And I'm just going to put down here that if it passes to the point -1, 0, then x is equal to -1 when y is equal to 0. And that allows us to find that constant. So substituting those values in, I get that 0 is equal to 2 times -1 cubed plus 3 times -1 squared plus that constant. That's what we're looking to solve for. That means that 0 is equal to -2 plus 3 plus a constant. If 0 is equal to 1 plus a constant, when I move that 1 to the other side, I get -1 is my constant. And that allows me to say that the particular solution to that differential and the initial condition is that y is equal to 2x squared, oops, Just messed up there a little bit. It's not squared, is it? It's cubed. So 2x cubed plus 3x squared minus 1. Our constant was -1. You could put plus -1, but it looks a little weird, so I would recommend kind of going to that default. And if you're adding -1, you're effectively just subtracting 1. This concept of parallel curves brings up the idea that several different equations, and really it's infinite different equations, could have the same differential equation. And we'll see that in a second here. But the idea is that when we get that general solution, really what we get is what we often call a family of functions that are parallel to each other. Now they define, curves being parallel as a constant vertical distance between the points. So if we took a function and subtracted the other function, we would always get 2, or we would always get 3, or some, constant value. And they demonstrate this by graphing 3 different functions. I'm not going to belabor how you would get these graphs too much. You could certainly use your calculator for this, but I am going to draw them kind of one after the other. So in black right here, I'm going to have my y is equal to 2x cubed plus 3x squared. With the 30-1 curriculum the way it is, most students are now able to kind of recognize that if we look at these 3 functions, then all we're doing is a vertical translation. So when I look at my next function, and I'm exaggerating this a little bit certainly, but what it would look like is something like this. And that's going to be the second function listed, which is y is equal to 2x cubed plus 3x squared minus 1. And then while I'm at it, I'll just finish the other and try to make that gap a little bit bigger. That this third function, something like this, would be y is equal to 2x cubed, run out of room here, but I'll fit it in, plus 3x squared, and then finally minus 3. Now, the idea behind these is that other than my bad drawing skills, these graphs have exactly the same shape. That means that they have the same slope at the same x value. They have, the same x value, at least for their local maxes and local mins, and they have the same end behavior. What the difference between these functions is that there is a constant vertical distance that I'm just going to label right here as essentially c. And if we look at these graphs, again, other than my bad drawing skills, trying not to judge too much, we see that that difference between the functions, again, bad drawing, but is relatively constant the entire way. And that's the idea behind parallel functions. And what I'd like to show that all 3 of these would have the same differential equation, which would be dy over dx is equal to 6x squared plus 6x. So all 3 of these functions have the same differential equation, but what we would notice is that the first graph, and I'll make sure I color code this correctly, the first graph passes through the origin, 0, 0. The graph in red passes through 0, -1, and the graph in blue passes through 0, -3. These, or what I've written on the far left, would be our initial condition. And what the initial condition allows us to do is it allows us to say, instead of just saying that it's 2x cubed plus 3x squared plus a constant, we can identify that constant. And it takes us from a general solution to a particular solution that satisfies a differential equation. The differential equation involves this Leibniz piece right here. The initial condition allows us to find that specific solution. We're going to do one more example here, and it is, everybody's favorite. It's Euler's number. It says, suppose for the graph of G, that every point, the derivative is equal to that. So that's just giving us a derivative, or a differential equation. It wants us to find the equation of a graph parallel to G that passes through the origin. Now, when you see parallel to G, it really just means that it has the same dy over dx, at least in this context, that's what it's referring to. And then if it passes through the origin, it's giving us the point, the origin, which is 0, 0. Now, a lot of students will fall into this pitfall of thinking that if it passes through the origin, the constant must be 0. And you do have to be a little bit careful because, technically that's true for polynomials. If the differential equation is a polynomial and it passes through the origin, then yes, the constant is 0. This is not a polynomial. Because it's e to the power of -x, I would highly recommend just following our process through. So if dy over dx is equal to e to the -x, then y is equal to -1 times e to the -x plus our constant of integration. And now that we know it goes through the origin, I can say that 0 must be equal to -1 times e to the -0 plus a constant. That 0 is equal to -1 times 1 plus that constant. If 0 is equal to -1 plus c, when I move that 1 to the other side, I get that 1 is equal to my constant of integration. And then I can say that my final solution is that y is equal to, oops, I forgot the negative, not a good start today. We're going to have negative e to the negative x plus 1. All right, 9.2 is really just about using that initial condition in order to narrow it down to a specific or particular solution. A lot of antiderivatives show up in 9.2 all over again. You need to practice those. You need to become comfortable with them because they really do form the backbone for this entire chapter. Please make sure you are trying these questions. And as always, email if you need any help and we can go through a few together.